Think fast. How quickly you can react to a given situation will determine how suitable you are for certain careers. Sudden change or deterioration in patient condition or an unexpected change in an operating room calls for quick action. Medical professionals are good examples of people who are called upon in a crisis to make a fast and highly accurate decision. Rushing to rescue a swimmer in trouble at the first cry for help is a moment that all lifeguards have trained for. Jet fighter pilots may avert danger by taking swift action against turbulence and wind shear, or may make instant adjustments to guide their plane to safety. Reaction time can mean the difference between scoring the winning touchdown or losing the big game. But different kinds of stimuli will elicit different reaction times. So this brings us to the question of which type of stimulus will lead to a faster reaction time, auditory or visual. Also, would the reaction time depend upon the spatial distribution of the stimulus? Based on the fact that light travels faster than sound, it was hypothesized that the reaction time for visual stimuli would be less than that of auditory stimuli. Since the left side of the brain controls the right side of the body, it was also hypothesized that stimuli perceived by the left ear or eye would elicit a faster response time by the right hand as compared to those received from the right side of the body. To test reaction time to a simple stimulus, we used a wiimote controller which communicated with the LabVIEW program. The first 3 trials were auditory stimuli in the following order: left, right, and random, with 5 stimuli for each. This was followed by 3 visual stimuli trials, again with left, right, and random. The duration between stimuli was randomized between 1 and 3 seconds to prevent subjects from anticipating the stimulus. During each of the tests, the subject was instructed to keep his or her focus on the center black dot on the screen and react to the noise stimulus or flashing red light on either side of the screen by pressing the A button. The subject was instructed to use the right hand to respond to the stimuli. All data was analyzed using the one-way ANOVA analysis. In the auditory left versus right graph, this figure shows the comparison in reaction time to auditory stimuli received from the left and right ear of the subject when the right hand was used to react. As can be seen, there was no significant difference in reaction time based on what ear the stimulus was perceived from. In the visual left versus right graph, the figure shows the comparison in reaction time to visual stimuli received from the left and right eye of the subject when the right hand was used to react. As can be seen, again there was no significant difference in reaction time based on what eye the stimulus was perceived from. In the audio versus visual graph, the figure shows the mean reaction time between auditory stimuli versus visual stimuli. The mean reaction time for auditory stimuli was 257 milliseconds, while the mean reaction time for visual stimuli was 327 milliseconds. The difference between these two means was statistically significant, as is shown. While the result that auditory response time was shorter than visual response time was not what we had originally hypothesized, it is generally supported by peer-reviewed literature. Numerous studies have shown that the response time to a simple visual stimulus tends to be 50 milliseconds slower than a simple auditory stimulus. Our results supported this, as we have found the visual response time to be 70 milliseconds slower than the auditory response time. This difference makes sense, as an auditory stimulus takes about 8 to 10 milliseconds to reach the brain, while a visual stimulus takes approximately 20 to 40 milliseconds to reach the brain. It was hypothesized that a user reacting with the right hand would experience a faster reaction time when responding to a stimulus from the left ear or eye due to the connectivity pathways of the brain. Our results did not support this, as no significant difference in reaction time was found based on the spatial distribution of the stimulus. Other studies have shown that the difference in brain processing time based on the left or right input tends to be as low as 10 milliseconds. Therefore, there may in fact be a difference in reaction time. However, because of the limitations in our sample size and measuring sensitivity, we were not able to detect a significant difference. Comparing visual and auditory stimulation processing to determine which is faster has many applications in safety devices. Automobiles and airplane warning systems could use data from this type of trial to better target not only which type of stimulus should be used, but also where it should appear relative to the user. We did not take into account stimulus intensity in this investigation, as the stimulus volume could be adjusted by the user to be comfortable. Future studies could take this factor into account, as it may significantly affect the results. Reaction time is also closely correlated with age, but because our subjects were college students of similar age, it was not considered a factor in this study. It was also observed that some subjects showed decreased reaction time over the course of the trials. This suggests that reaction time can be minimized by practice and neural pathway familiarity. Future studies could investigate this as it presents significance for athletes and other professions.